Hello everyone, myself Sushma Shetty, B.Ed first year student from KLS College of Education, Ankola. So today we'll discuss about interesting mathematics topic, that is real numbers. Let's begin. In your earlier classes, you might have studied about real numbers. What is real numbers then? We have studied about many types of numbers as natural numbers, whole numbers, rational numbers, irrational numbers, fractions, decimal numbers. All these comprised together are called as real numbers. Let's see one by one. Natural numbers. Natural numbers are the set of counting numbers which starts from 1. They are denoted by n. For example, 1, 2, 3, etc. Whole numbers. Whole numbers are the set of numbers that include 0 plus the set of natural numbers. For example, 0, 1, 2, 3, 4, 5, etc. That means 0 is added to natural number, that itself. Integers. An integer is a whole number, not a fractional numbers that can be positive, negative or 0. It is denoted by z. For example, z equals to minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Next comes rational numbers. Rational numbers are any numbers that can be expressed in a form of a by b, where a and b are integers and b is not equals to 0. They can always be expressed by using terminating decimals or repeating decimals. For example, 2 by 3, 6 by 7, 1. Next comes terminating decimals. Terminating decimals are decimals that can contain a finite number of digits. For example, 36.8 or 0.125 or 4.5. Repeating decimals. Repeating decimals are decimals that contain infinite number of digits. For example, 0.333, etc. 7.689689. Non-terminating decimals. While expressing a fraction into a decimal by the division method, if the division process continues indefinitely and zero remainder is never obtained, then such a decimal is called a non-terminating decimal. Or we can say in a simple words, a non-terminating decimal is a decimal never repeats. For example, 0.076923 or 0.05882352 and all. Next comes Euclid division lemma. Statement. For any two given positive integers a and b, there exist a unique integers q and r satisfying a is equal to bq plus r. 0 is less than or equals to r less than b. For example, let me have two numbers 455 and 42. Then 455 equals to 42 into 10 plus 35. When 455 is divided by 42, then 455 will be the dividend, 42 is divisor, 10 is quotient and 35 is remainder here. Euclid's division lemma is a technique to compute highest common factor HCF of two given numbers. You might be familiar with the term HCF here. It is based on the fact that dividend which is equals to divisor into quotient plus remainder. If we compare both, we find a equals to bq plus r. So dividend is a, that is a is dividend, b is divisor, q is quotient and r is remainder. Hence when r becomes 0, then last divisor is the HCF of a and b here. Let's take an example here. To find HCF of 135 and 225, greater number is 225. So dividing it by 135, the smaller number. So 225 equals to 135 into 1 plus 90. So 225 is the dividend here and 135 is the divisor and 1 is the quotient plus 90 is the remainder. Now next 135 is to be divided by 90. 135 equals to 90 into 1 plus 45. Again 90 is to be divided by 45. 90 equals to 45 into 2 plus 0. So when the remainder comes 0, the last divisor will be 45. So the HCF will be 45. So HCF of 135 and 225 is 45. An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. A lemma is a proven statement used for proving another statement. So let's see. Euclid division algorithm now. Algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Euclid division algorithm can be used to find the HCF of two numbers. It can also be used to find some common properties of numbers. To obtain the HCF of two positive integers, say C and D, with C is more than D, we have to follow the steps below. Steps 1. Apply Euclid division lemma to C and D, so we find whole numbers Q and R such that C equals to DQ plus R. Step 2. If R equals to 0, D is the HCF of C and D. If R does not equals to 0, apply the division lemma to D and R. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be required HCF. So there is 3 steps in the Euclid division algorithm. Comparison between Euclid's division lemma and long division method. To understand the similarity between Euclid's division lemma and long division method for finding HCF, let's take an example. To find the HCF of 12,576 and 4,052. So when 12,576 is divided by 4,052, so here comes 3 is quotient plus 420 is remainder. In the first step. And the second step, when the 4050 is an dividend and 420 is an divisor and 9 is quotient here and 272 is remainder. Third step, 420 is the dividend and 272 is an divisor, into 1 is quotient plus 148 is remainder. So we have to follow the same step till we get the remainder 0. See here, when in the last step 24 is the dividend here, divisor is 4 and 6 is quotient plus remainder is 0. So in the last step remainder is 0. So now the HCF is 4. Both the cases are exactly same with the just difference in method of expression, that itself. So similar example, find HCF of 196 and 38,220. So bigger number will be the dividend, 39,220 when it is divided by 196. So 196 is a divisor here, into 195 is the quotient plus remainder is 0. Last divisor equals to 196. So HCF is 196. Find HCF of 867 and 255. 867 will be the dividend, 255 is divisor, into 3 is quotient plus 102 is remainder. Next step, 255 will be the dividend, 102 will be the divisor, 2 is the quotient and 51 is the remainder here. So in the last step, 102 will be the dividend, 51 will be the divisor, into 2 is quotient plus 0 is remainder. When the remainder comes 0, so we will consider the last divisor, that is HCF 51. So the HCF of 867 and 255 is 51. Next, moving on to fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes. This representation is called as prime factorization of the number. This factorization is unique apart from the order in which the prime factors occurs. When the 1092 is done with prime factorization, so circle the primes as they appear. 2, 3, 2, 7. These are the 2, 3, 2, 7 and 13 are the prime factors here. Highest common factors HCF, lowest common multiple LCM. The highest common factors of two numbers is equal to the product of terms containing the least powers of common prime factors of the two numbers. The LCM, that is lowest common multiple of two numbers, is equal to the product of terms containing the greatest powers of all the prime factors of the two numbers. So this is the difference between highest common factors and lowest common multiple. So let's see the relation of LCM and HCF with two numbers. HCF of two numbers is a product of smallest power of each common prime factors in the number. LCM of two numbers is a product of greatest power of each prime factors involved in the number. For any two positive integers a and b, HCF that is AB into LCM AB, which is equals to A into B. Now HCF and LCM type questions. Find the HCF of 96 and 404 by prime factorization method, hence find its LCM. So first we have to find HCF of 96 and 404 by prime factorization. Then we have to find LCM here. The prime factorization of 96 and 404 are 96, which is equals to 2 raised to 5 into 3. 404 2 raised to 2 into 101. So therefore the HCF of these two integers is 2 raised to 2, that is 4. As we know how to find this HCF. As we have seen in the previous slide, what is the formula there? HCF A B into LCM AB, which is equals to A into B. We know HCF of 96 and 404, that is 4, right? We have to find LCM of 96 and 404. So 4 into LCM of 96 404, which is equals to 96 and 404. So 96 LCM of 96 404, this 4 we have to take it in a right side. 96 into 404 divided by 4, which is equals to 9696. So this is the LCM of 96 and 404. Next comes irrational numbers. Irrational numbers are any numbers that cannot be expressed as A by B. So we have studied in the previous slide, that is about rational numbers. What is rational numbers? Rational numbers are any numbers that can be expressed as A by B. So irrational numbers are any numbers that cannot be expressed as A by B. They are expressed as non-terminating, non-repeating decimals. Decimals that go on forever without repeating a pattern. Examples of irrational number: 0.343343334, something that, and 45.86745893, and pi. Pi is the best example for irrational numbers, and root 2. So these are the example for the irrational numbers which cannot be expressed in A by B form. So next, proof of sum of irrational numbers. Theorem: let P be a prime number if P divides A square, then P divides A, where A is a positive integers. Proof: let the prime factorization of A be as follows. A equals to P1, P2, P3 up to Pn, where P1, P2, P3 up to Pn are primes, not necessarily distinct. Therefore, A square equals to P1, P2, P3 up to Pn into P1, P2, P3 up to Pn. That is, A is P1, P2, P3 up to Pn. A square means double of it. Now we are given that P divides A square. Therefore, from the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square. So clearly P is one of P1, P2, P3 up to Pn. Since A is equals to P1, P2, P3 up to Pn, P divides A here. So next theorem, that is root 2 is an irrational number. How to prove this root 2 is an irrational number? Let us assume to a contradictory that root 2 is an rational. So we can find integers A and B which is not equals to 0, such that root 2 equals to A by B, where A and B are co-prime numbers. So B root 2 equals to A. So cross multiplication, that is root 2 equals to A by B, P root 2 equals to A. So squaring both sides and rearranging, we get 2B square equals to A square. Root 2 square means 2. B square is B square, which is equals to A square. So 2 divides A square here. Now by theorem 1.3, that is previous theorem, it follows that 2 divides A. P divides A means here P is 2. 2 divides A. So we can write A equals to 2C for some integer C. Substituting for A, we get 2B square equals to 4C square. That is B square equals to 2C square. This means 2 divides B square, and so 2 divides B here from previous theorem. Therefore, A and B have at least 2 as a common factors, but this contradicts the fact that A and B have no 2 common factors other than 1. This contradiction has arisen because of incorrect assumption. So we conclude that root 2 is an irrational number. Rational numbers and their decimal expansion. Theorem: Let x be a rational number whose decimal expansion terminates, then x can be expressed in a form of p by q where p and q are co-prime and the prime factorization of q is of the form 2 raised to n 5 raised to m where n and m are non-negative integers. Any rational numbers of a form a by b where b is the power of 10 will have a terminating decimal expression. Let's take an example. 3 by 8, that is 3 by 8 means 2 cube. So 3 into 5 cube divided by 2 cube into 5 cube. 3 into 5 cube is 375. 2 cube into 5 cube is, that is 10 cube, which is equals to 0.375. Some other theorems are like, let x equals to p by q be a rational number such that the prime factorization of q is of form 2 raised to n 5 raised to m where n and m are non-negative integers. Then x has a decimal expansion with terminates. This is one kind of theorem. So another theorem like, let x equals to p by q be a rational number such that the prime factorization of q is not of form 2 raised to n 5 raised to m where n and m are non-negative integers. So then x has a decimal expansion which is terminating or non-terminating repeating. What is the difference between these two theorems? So x equals to p by q is the rational numbers in both the case such that the prime factorization of q is of form in previous theorem, that is q is of form 2 raised to n 5 raised to m. In second theorem, the q is not in a form of 2 raised to n 5 raised to m. So these are the important theorems. Thank you for watching.